Just to reinforce, what we did, I have some classwork activity based on that homework, and I'm going to pass this around, and we'll just spend the first half of class working on these, and you can work together and use the psychometric chart. Yeah, but I'm just going to collect your answers. So if you read the instructions, just you can work in pairs and write your name on a separate sheet of paper. And what I'd like you to do is turn in just your answers, and I'm going to collect this for classwork. But you can keep your work. This is just practice to make sure we're all getting the how to do these problems. I think you will need the water table, the water properties table. So if you have your book or if you have my notes, well, I don't know if my notes have them, but I can pull it up.
Either way. You want to work them together?
Yeah. So problem 4 really moves us into the material for today, where we start to calculate energy and mass flow and air conditioning processes. Simple air conditioning, heating, cooling, humidification, dehumidification. And how we represent those processes on the psychometric chart, and how we apply the first law to figure out how much heat are we putting in, how much are we taking out, and so on. And then once we learn these basic air conditioning processes, we'll put them together to make more complex and realistic air conditioning systems.
You can just assume a certain amount. So what I'm going to do is I'm just going to assume 100 pound mass, and then I'll go through and nitrogen's N2, correct? N2, and then oxygen's O2. Okay. And then what we do is we'll find the mole fraction of each. So we'll take the pound mass of and then the amount of the molar mass in pound mass per pound mole of nitrogen. So 28.006 pound mass of O2 per pound mole. So this will give us pound moles each, if that makes any sense. And then what we're looking for is we're looking for the molar fraction. But first we need to calculate the total number of moles. So 22.15 divided by 28.06.
So what's that's percent, right? Oh, okay.
No, this is how many moles.
Okay, so you have 23%. So you change to that to mass, right?
Yeah, so-
0.23.
Yeah, so what I did is you just assume there's a certain amount. So you can assume any value. I did 100 because 100 is easier because it's in percentage,
Yeah.
or it's given in percentages. So nitrogen is 20. Oops, I just did that wrong anyway, so I gotta redo it. I just used the nitrogen value for oxygen, which isn't right. So oxygen is 32, so this is gonna be a smaller value. Here we solve this. And then once we get this, what this gives is this will give the total. Okay, so 7.
Professor Cobb,
Yes.
I get the.
Oh, yes, sir.
Thank you.
Chart.
7. So we're looking at, this is oxygen, so
Just 1 minus that one.
no, so what we're doing is what you do is you're finding the amount of pound mole for both oxygen and nitrogen is on the bottom, because that's the total amount of moles, or pound moles for the entire mixture, and then you divide by how many are in or you take how many are in oxygen, and then you divide by how many are in oxygen and nitrogen, if that makes sense. So the mole fraction is 0.2087. If that makes sense. And then this is by 14.7 ESIA.
Never.
Okay.
And now we should find the copy question.
Yeah. Yeah, so that would be equal to the mole fraction times
For each one.
so we're only looking for the oxygen one. It doesn't ask for the nitrogen one, I believe.
So oxygen divided by the total amount of 1 mole.
Yeah. Yeah. Yeah, so I got a little over 3 psi because we're finding pound moles. I don't care, that's total. You want to know how much, what percentage of the pound moles are for oxygen, if that makes sense.
Oh, got the tables there.
Okay, so we're given relative humidity.
We have 10%. I think nobody's multiplied with percentage by pressure.
Yeah, so we can find the pressure of water, and then we can back out the.
This I think it's
Yeah,
going to
so
be 0.12.
Yeah, so we can
What's
find,
saturated for 120?
because that's the water vapor.
Yeah, it's 104.
But that would be the water vapor. Oh, and then we can just subtract.
Yeah.
Yeah, I see what you're saying. That makes more sense. Alright. So this would be PW, and that would be P saturated at, this would be saturation at 104 degrees Fahrenheit. So I can look this up in the table.
Table is here.
You do find it in the question.
I've got it right here. It should be, it's, so we're looking, oops, this should be, so it's gonna be 2.3.
No, right? Just,
Yeah, I think I did. I think you're correct. Yes, we want.
So when you see gases mentioned like nitrogen,
So we're at 104. 104.
oxygen,
is,
hydrogen,
0710 PSIA.
yeah, especially these
Okay.
gases, they are almost always in a diatomic form. So nitrogen is almost always going to be N2, oxygen, O2, hydrogen, H2. So when you look up the molar mass, be sure that you're looking it up for H2, O2, and N2, not just N by itself or O by itself. These gases really only exist for momentarily as single atoms, and they're highly unstable, and they'll quickly react with something else to form a more stable compound. Now, oxygen will break up in under the influence of solar
Yeah,
radiation in
so-
the atmosphere into O2 minus, and then it'll form ozone, which is O3. And a reaction that we try to avoid is when a single oxygen reacts with a single nitrogen to make nitrogen oxide. That forms smog in the atmosphere. But this kind of reaction generally only happens at very high temperatures. It happens in combustion, for example, of fossil fuel. But nitrogen, just by itself like that, just doesn't really exist for the most part, except in very unusual circumstances.
Yeah, so it's 14.
Even more so with hydrogen and oxygen.
Yes. So it's this. So, or close to that. Yeah.
To avoid any confusion, it's always good practice just to write out the empirical formula or the molecular formula as well as the name. I think I just mentioned the name.
And now I think we should use this one.
Yeah.
Yes.
So, yeah, it would be better just to
The bigger
write
one or
the
smaller?
formula beside the name so that there isn't any
Probably a larger
confusion.
one since we did.
I think maybe the larger one for the hard exercise.
Oh, yeah, it's a good one. Oh,
Yes.
For the larger train chart, is this supposed to be for the classwork or for the exercise later?
That's for the problems 3 and 4.
oh, okay. Okay, sounds good. Thank you.
Yeah. And
Just write this down.
I think.
number here that's in degrees. And so here, you know, 144 degrees. So you multiply this by 7,000. It's 144. Yeah, so that's the conversion. Just a lot. Some people like working.
Writing it down.
This number
But
is
yeah.
more a reasonable number as opposed to really small. Yes.
Yeah. Yeah, so, hold on, so before we do that, I think the easier thing to do would be to draw, it says humidity ratio of 0.0206. So what we're trying to do is, well, I agree, we'll go to the 60 curve, so 0. Humidity ratio. That's it's not vapor pressure.
Sometimes you will see 40
Oh, it's in grains. Yeah, so we need to convert. So you multiply by 7,000. You have to multiply by 7,000. Yeah, so it's, yeah, so you have to multiply 144 grains. He wrote it right here. It's already been converted. So we have to find 144. So it'd be one, yeah. So 144 would be here, and then we would draw this across, and then we would find where the 60% curve goes. So 60% here. So
Yeah, so and we can get a chart.
yeah, it's hard to. Yeah.
So
You want to read it? It's up, we can up.
It'd be 144 would be right here. It says 148. It's supposed to be 144.
Oh, yes.
No, don't worry. Yeah. I see what you're saying. It's difficult to see with the. Let's do this so we can see it. So then we're looking for when this. We're looking for when this goes. So 60% is this curve, so it's right here. It's that point. That's the point we're looking at.
Well, we're just debating like as far as.
So now you have to read off all the properties.
If we did it as an atomic mass, then get a molar fraction.
Oops. Yeah, go ahead. Yeah, of course. Yep. Feel free to use the pen if you want to.
It's the great concept. We want the physics.
You have to relate it to mass, right?
Yep.
you have to relate it to moles.
Yep.
So
Yep. Okay, so now we can start reading things off. So the temperature is at is. So if we draw it down. So temperatures. It looks like this 91, 92, 93. So about 93. Because I just drew it straight down. We're supposed to draw it straight down, I think so, yeah. Yes, I do 93. So dry bulb is 93. So, dry bulb is 93 degrees Fahrenheit. What do you want to find next?
Okay.
Enthalpy, it says? Yeah, enthalpy is huge. So we're oh, that's a bummer. Mine's not long enough to draw.
I just found from the mixture table, is the absolute pressure, for water, that saturation for pressure for, like gas
Okay. No, it was a little bit hard. I'm trying to see if I can. Actually, so okay, that's there. That's trying to line up to 45. Actually, I think it's just about 40. You can just call it 45.
Those of you in the FE prep class, questions 1 and 2 are actually good questions for the FE exam on the thermo part that we'll be covering this Friday. So you might see questions like this in more than one situation.
I think I was slightly off. I think it's 45.
Yep.
Yeah, I'll just, I can erase the bottom. Okay. Yeah. Close enough. Yeah. 45.1. That's about as close as we could get. Yeah, I mean, it's a little bit high, so we could say, what, 40,
40.
45, 45.1, somewhere around there. 45's right here.
Oh, sorry.
Yeah.
40, 45.
Yeah. I think so. I think I'm a little bit high on the.
That's good. No problem.
No, I think you're right. I think I just can't get it to draw as good with the. Yeah, we can say 45.1. All right. Bless you. 45.1 BTU per pound mass dry air. Okay. Specific volume. That's 14.4. That's 14.5.
I forgot to send you the, sorry about that. Been so busy.
I'm honestly not for sure. I'm gonna say 14.1, 14.2, somewhere around there. Or not 1, excuse me, 4.1, 4.2. Is that what you're thinking?
Yeah. Yeah, 14.42.
4.2, okay. Or 4.1, I don't know. Okay. Let's say 4.1. And this is cubic feet per pound mass dry air.
Before I forget, I'll collect your homework now if you'd like to give it to me.
Okay. Enthalpy, specific volume, wet bulb temperature. So we need to find the wet bulb. So 85, 90. This is going to get a little bit more difficult to see. So 85.
Is that homework over here? Okay. All right, I can. Oh, okay, great. That's.
Thank you. Oh, you want to have your number? Oh, okay. Okay. So we just need to, we need to figure out the wet bulb.
I will need a
Oh.
So this is 80, 81, 82. So I'd say about 81 and a half.
I'll have a stapler.
Do you agree?
Yeah, I'll just keep it
Okay.
together.
I
until
just
I
had
get
to
it.
add this.
Another name on this.
Determine the dry bulb temperature, enthalpy, specific volume, wet bulb temperature. Yes, so we just did that.
Okay, do I have all the homework?
So we're done with number 3. So we gotta do number 4. It looks like problem 4 is connected.
No, you're fine.
Oh, Dr. Collins?
Mhm.
So we're supposed to do up through problem 4, and then this last part, are we gonna do together?
Yeah, and we can do problem 4 together as well, because that sort of transitions to today's
Okay.
material.
So just get to problem 3.
Get through problem 3,
Okay.
and then you'll be current.
Okay, so we can write our answers down if you feel good about that.
Yep.
Okay, good. I'll write this down so we have the next one, but
And
yes.
if you want to try problem 4,
You guys submit that one or just what sheet of paper?
We could just do the answers if you want.
Okay, let's see.
If you want, after, since if you haven't written down as much, I could also just send you a note of this too.
Yeah.
Yeah, if that helps.
Just write, just put the.
The answers, okay. Oh, I see. Yeah, we haven't done one of these.
Which one?
We haven't done one of these yet. Okay,
Oh,
that
okay,
makes
that's
sense.
why
So,
he wants to,
yeah, because the thing is, if you dehumidify, you go down.
Yeah.
If you cool, you go to the left. So what we're doing is we're going to the left and going down. So we haven't done that before. I think I see that. Okay.
That's really nice now. You can make straight lines and move the lines. Probably not.
Your other classes?
Today now.
I tried.
Yeah, one of the things we also.
So this is the
have
only
to
class
do
you have
is
today?
Find the
Oh,
slope.
have your other classes been posted this week?
We have to,
What did you say?
Have your other classes been
we have to
posted?
define a slope, and then with a straight edge, and then move it across the chart, keeping that slope constant. It's really hard to do. You have to have a protractor, multiple straight edges. And if you're doing it on the computer, it's just really easy.
Yeah, I apologize. Didn't have a longer ruler. That's just the smaller one. That's the smaller one I have. That's good. Dr. Cole, I wanted to ask, just conceptually, for where it says what is rate of heat removal, that would be both sensible and latent, correct? So it'd be like the triangle part between latent and then sensible? Okay, okay, thank you.
Yeah.
I think that was explained in the video that you posted.
Yeah, it's the triangle part, but it's a little bit deceptive because it's not the hypotenuse, or you don't calculate it like the hypotenuse. It's actually the real sum of the sides. QL plus QS.
Okay, but it's just represented like a triangle.
Yeah.
Okay.
Yeah. Yes, sir.
Okay, thank you. Do you want to wait until we get to that in the class?
Sorry about that. I actually
For question 4?
So do what?
Oh, just wait still
Oh, okay.
until he explains it? Okay. What is the rate of water removal in some water. Okay. Okay. I guess we just write our answers down.
Yep.
Do you want me to do that, or?
Oh, you want, oh,
Okay.
to have, I mean, I don't have any piece of paper.
I can give you one. He just mentioned to write our names on that, so we can just write both of our names. Yep. There you go. So yeah, I think we just have to put our names, and then he said, write your names. Okay.
Just writing here.
Oh, okay. Right. And then I think it said we're supposed to only put the answer. Yeah, write your names on a separate piece of paper, write the problems below, and write only the answers. So instead of writing them out, do you want to should we just write 1, 2, 3 instead? If you want, okay. Actually, to be honest, do you like this chart better than the actual? Because even though it reads in grains, you'd have to convert. Do you think it's easier to use? Because this is the train, I believe. This is the asteroid.
Okay, number one.
3.06, 3.07, something like that. I don't know. I said 0679, but that might be overkill with a number of sig figs, but that's okay. PSIA. Second one was 14.364. Pen or pencil? 364 PSIA, and then the 3 dry bulb temperature was 93 degrees Fahrenheit. Enthalpy was 45.1 BTU per pound mass of dry air.
For number two, right?
Yeah. So we have dry bulb temperature. Enthalpy was 45.1. And then I would just say, after that, just say BTU per pound mass of dry air. I don't think we have to write out the other part. I don't worry. That's fine. The lead is kind of thin anyway. Yeah, so 45.1 BTU per pound mass of dry air. And then specific volume, we have 14.41 cubic feet per pound mass of dry air. 14.41 cubic feet per pound mass of dry air. And then the wet bulb temperature, we said, was 81.5 degrees Fahrenheit. 5 degrees Fahrenheit. Yeah. Okay. Yep, I think that's it. Yeah, no problem.
All right, you wanna, how about if we start, we'll go over them.
Hey, good job, that's good.
So problem 1, we're given the mass percentage of air. It's a 2-component mixture. And really probably the easiest way to handle a problem like this is just to assume that we have 100 pounds, or 100 grams, or 100 kilograms of the gas. And so we'll assume a 100-pound basis. Assume 100 pounds of mixture. And then we can just make, our mixture can consist of 23.15 pounds of oxygen and 76.85 pounds of nitrogen. Okay, so that sum is gonna be 100. Okay, so now we want to convert to moles. So we're in the pound mole system. So pound mole of O2 would be equal to 1.5 pounds of O2, and we would divide by the molar mass, which is 32. And that's going to give us how many moles of O2 are in 23.15 pounds. And that turns out to be 0.7234.
Yes.
And then the same thing with nitrogen. So pound mole of N2 would be 76.85 pound mass of N2 divided by 28 pound mass in a mole of N2. And that gives us 2.7446 pound mole of N2. And now we add these to find out how many moles, total moles, we would have in 100 pounds of the mixture. Pound mass. I stopped using pound mass because we don't use the M in HVAC work. But because I teach thermo, we do use pound mass. And I actually like to make clear because it's easy to confuse when we're talking pound mass, pound moles. If you just write pounds, it can be unclear. But in HVAC, we almost never use pound force, unless we're talking pressure. But then we just say PSI, PSIA. But anyway, pound mass and pound mole. So we add them up and we get 3.4680 pound mole of our mixture. Okay? And what we're looking for here is partial pressure. Probably should have written this out first, is that the partial pressure of the gas, in this case O2, is going to be equal to the mole fraction of O2 times the total pressure, right? Definition of partial pressure for an ideal gas, or a mixture of ideal gases. So we could also write this as the pound moles, or moles of O2 over the moles of mix times the total pressure. Okay, so what is YO2? YO2 is moles of O2 over the moles of the mix, and that's equal to 0.7234 divided by 3.4680, or 0.2086. So our mixture is about 20%, 21% oxygen by moles, on a molar basis. So then our pressure, partial pressure of O2, is equal to 0.2086 times the total pressure, which is 14.7 psi. A gives us 3.066. Okay? I think on your homework you had just a 3-gas mixture, so it's a little more work. Probably on an exam, it would be a 2-gas mixture just to cut down on the busy work. 3.06. 6. Okay? Now the second problem is sort of related to that. We just add humidity, relative humidity to the mix. And relative humidity by definition relative humidity is the ratio of the partial pressure of the water vapor in the air to the saturation pressure at the dry bulb temperature. So the partial pressure of the water vapor in the air to the saturation pressure at the given temperature. And in this problem, the temperature is 104 degrees. Technically we talk about relative humidity as in percentage terms, is the conventional word term for it. So, but in calculations we always use it as a decimal. Okay, so the temperature is 104 degrees. The saturation pressure of water vapor at 104 degrees is equal to, and here's where we have to look this up in the saturation table, which I cut off. Get it back on. Yeah, it doesn't like to just sit being turned on, automatically turn off. But the saturation pressure, anybody get a value for that?
1.0710.
What did you get?
1.0710.
1.0710?
Here.
The value that I got, 1.07088. I think I got that out of our thermo textbook. But if you have our thermo textbook, you can find the same information in the saturated water table in the back of that book. I use that sometimes as well. I like the way that textbook lays out the tables and really easy to read. But 1.0710, that's fine. So that would be at 104 degrees. We would have saturated vapor at a pressure of 1.0710. And if we reduce this pressure, then it's gonna become superheated. It's gonna become superheated vapor. So it's got this situation here. Temperature is 104 degrees. So saturation would be right there. We have saturated water vapor. When we're at that point we're on the saturated vapor curve, and the temperature is 104 degrees, and that pressure, this line of constant pressure would be 1.0710 psi-A. And if we go down, as we go down in pressure, so if we reduce the pressure, keeping the temperature constant, we would go that way, and we become superheated, right? And that's where our actual pressure is. Our actual pressure is going to be somewhere out here. So we need to know any two of those quantities, and we can calculate the third. In this case, we have the humidity is 22%. Psat is 1.07, so we can calculate the partial pressure of the water vapor as the humidity times the saturation pressure, or 0.22 times 1.0710 PSIA, and that gives us 0.2356. PSIA. Now that's the partial pressure of the water vapor, and we could use this to find the humidity ratio if we needed that. But in this case, we have to be careful to see what we're looking for, what it's asking for. It's asking us for what? Partial pressure of the dry air. And because this is an air-water mixture, the pressure of the air is going to be the sum of the partial pressure of the dry air plus the partial pressure of the water vapor. So if we're looking for the partial pressure of the dry air, it's just going to be the total pressure minus the partial pressure of the water vapor, or 14.6 minus 0.2356 is 14.36. In other words, the air is overwhelmingly, it's overwhelmingly dry air with a little tiny bit of water vapor floating around in it. But that tiny bit of water vapor is a lot of what air conditioning is all about, because that water vapor has a lot of energy. It's superheated vapor, so it has a lot of energy in it. And it takes significant cooling systems to remove that water vapor, especially in humid climates. And you're designing buildings in Florida or Washington, D.C. Wow, all of that humidity in the air really imposes an energy cost on your air conditioning systems. Okay, so those are some calculations. Now we get to the fun stuff here with this psychrometric chart. Let's see if we can get this on. Probably better to all right, so that's a little blur, isn't it? I guess we can make it out. When I use this on slides, when I'm teaching online, and when I make videos, I lighten this. I make it considerably lighter so you can see the writing on top of it better. But because these lines are so dark, it's kind of hard to use a pencil. You can lose, have a hard time seeing your own lines on there. But anyway, okay, so we're going to locate a given air state here, and this air is, we're given two properties. We need to know two properties of the air to fix the state, and we're given some odd, usually we're not given these two properties. Usually we always know the dry bulb temperature at least, because that's the easiest thing to measure, but here the dry bulb is a mystery. We have to find it given, what are we given here? The
Humidity ratio.
Relative humidity is 60%. And humidity ratio is 0.0206, 0206 pounds of water per pound of dry air. And because we're using the train chart is showing us the grains of water per pound of dry air along this scale, and that allows the use of larger numbers, so they're not really tiny decimal numbers. But to get to the grains, equals 7,000 is the conversion. So we multiply 7,000 times 0.0206, we get 144 grains of water per pound of dry air, okay? All right, so 60% humidity, that's not hard to find because, that's these green curves that sweep across like that. Then we have to find 144 grains. And to me, this is a lot easier to see and read on the train chart than it is on the hash rate. So here's what we're looking for. This is the scale, see humidity ratio, grains. So it's these numbers here. You see 130, 140, 150, and then each of the lighter lines here, it represents 2 units, 142, 144, 146, 148, 150. Here's 144 right there. So make a straight line. I need a longer ruler, longer straight edge. It's right along that line there. So that's 144. And I want to go all the way over to 60%. Here it is. Here's a 60% line. And bingo, it's right there. So what's the dry bulb temperature? We want to read down, straight down, to the bottom axis here. And it looks like 90, 91, so here's 90, 95, 100, 91, 92, 93, about 93.5. And generally, we can read the temperature, dry bulb temperature in units of, 90, 91, 90.5. I think to the 10th place is fine. Even it's hard to get to a finer grain than 90, 90.5, 91, 91.5, 92. I suppose you could split hairs if you're really careful and get to a 90.2, but 91, 92, 93.5 is good enough for 10th place. So dry bulb is 93.5 degrees F. How about the wet bulb temperature? What did you get for a wet bulb?
81 and a half.
81 and a half? Okay. So here's the wet bulb here. See wet bulb temperature. So those lines go down and to the right. And so you just want to find a line close to where we are. So there's 80, which means that's 81. That's 82. So we're in between 81 and 82. It's nice to have a computer doing this on the computer because you can move the lines, keep the slope the same. So it looks like about 81, 80, 81, 82, 81.4. 81.4. Let's see, what else can we do? Dew point temperature. What do you get for dew point temperature? How do we get that?
Well, this one's easy because you can just go to the right from, it shows, on the same column where we found the grains.
Go this way?
Yeah, all the way over, because it has the grains, but it also shows the dew point right there. But in the other chart, we had to go all the way over to the left, see where it crosses the saturation.
Yeah, so here we have a choice. We can go either way. We just need to go horizontal. The dew point temperature is reached in a constant moisture cooling, or adiabatic cooling at constant pressure, which means we go horizontal to the left until we hit the saturation curve, and that's going to be the dew point. As soon as we hit that, we start to condense water out of the air, and it looks like that is about 76, 77, 77 and a half. And if I read over here, 75, it's easier on this side, 75, 60, 77, 78, so 75, 76, 70, so that's 77, so it's about 77.5 exactly. Right?
Oh, no.
Yeah.
Oh.
Right? And at the dew point, when we get to the dew point, then all those temperatures are the same. They would all be 77.5, right? When we're at that point there.
Yeah, so this was.
Okay? And anything else? Let's see, there's a specific volume. What do you make of that?
So we have 14.4.
Yeah, that's about right. So here's a specific volume. So 14.2, 14.1, 14.2, 14.3, and this would be 14.4, 14.5, so we're just a little to the right of 14.4, so 14.41, 14.42, or yeah, I think we had 14.42, but 14.41, 14.42. And the last digit's always going to be uncertain. Okay? And then our favorite one. The most important one, but also the most difficult one to read off. Although I think it's easier on this one than it is on, well, I don't know. It's hard, it's got pain on this one as well, but we've got to, let's clean this up a little bit. And I'm afraid my straight edge isn't going to cut it here. We need to. Yes. Oh, thank you. Oh, man, that's great. Perfect. So this is what I like to do is I try to line up the two axes, the one over here and then the one on this side, or down here is enthalpy. And then, let's see, that's vapor pressure, so we don't want that. Enthalpy is this one here. So this is, if I line up 45 and 45, I'm right there. And that's really close, isn't it? 45 to 45. Maybe move it up a little bit. Something like that. Looks like about 45 point. Now I've got to figure out what is one of these little increments here. 40, 41, 42, 43, 44, 45, 40.5. Each one of these is 0.1. So I would say 45.1 or 45.2. How did you all read it?
45.
45 point. Let's see, when I did it, I had 45.2. Here it looks more like 45.1. again, you know, this is going to be a little bit uncertain here, and that's BTU per pound of dry air. Did we cover everything? I think that's about everything that we would need in a, you know, to characterize room air for air conditioning design calculations. Really, the main ones we need, the humidity ratio and the enthalpy. Those are the two key, the ones we most need. We need specific volume in order to convert volume flow to mass flow. And these other ones are not so much used in calculations. Although dry bulb temperature we use when we have mixing of two air streams. The dry bulb temperature factors in. And it's always a nice one to have because it's easy to look up. It's just, you know, it's right there on the bottom. Yeah. Is that the only thing we had on that one? Yes. Yeah. So number 4 moves us into material for today. So we'll take a little break here, and then we'll work number 4 together, and then we'll use that as a springboard to talk about air conditioning processes. Now I feel like a traditional teacher, a school teacher, headmaster.
Start sleeping.
Yeah.
Why?
Yeah. Shelby, put out your hand. Been a naughty boy.
Make sure to isolate that one every class.
It's really nasty air. It's outdoor air that's very hot and humid, almost as bad as it gets. Well, in terms of the combination of heat and humidity, I mean, we're way up there at the top of the chart. 60%. This enthalpy that's about as high as I've ever seen. I'm sure you can find higher in Phoenix or Houston, Texas, or someplace like that, but I haven't done work in places like that. But even here, well, when we design our air conditioning systems, we design for an almost worst case scenario. So if you're thinking, how do I size my system? What capacity do I design for? You pick the hottest day. Actually, it's not the hottest day on record. What you do, ASHRAE has a standard. You choose the day that is, how do you say it? It's 96.4%. So on 96.4% of the time in a year, 96.4% of a year, the temperature will be less than what you designed for. So there will be extremes in the 0.4%. And similarly on the heating side, when you're designing for cold, you would design for an almost coldest day. And I think in Seattle it's around 18 degrees or something, maybe low 20s, but which is relatively mild compared to other parts of the country, interior parts where it can get really, really cold. So that's going to determine how big, what the capacity of our system has to be. Then we just have to make sure we have a control system that can deliver less or more heating and cooling as needed given the outdoor conditions. So it means most of the time, the vast majority of the time, our air conditioning systems are not being operated according to their design because we design for the worst case. This is unusual, I think, in engineering design. Is most of the time our clients are using our equipment outside of the conditions they were designed for, and that's just the nature of the beast. You just try to put on, have a sophisticated enough control system so you can still operate efficiently as possible, even when it's not burning hot outside, absolutely frigid. But anyway, this is a pretty bad situation. Now, this is a hypothetical case just to get us used to the calculations and see what it's like. So we're going to take this air and we want to get it to an indoor state, a comfortable state, and because we call the air in our space The subscript that we use is R for return air. That's the space temperature. It's because that's the temperature at which the air is being drawn into the air HC system. So there's a return air vent somewhere that's drawing air out of the room, and that air is at what our design temperature is. In this case, it's going to be 72 degrees and 50% relative humidity. Is that right?
Sounds correct.
Final say, yeah. So this is a typical design state. Maybe a more energy conscious client will say 75 degrees is fine. But I like cool. I like cooler. 75 is not comfortable to me, but 72 feels better. 68 even better. I remember after college, sharing a room, had a roommate, and it was in Virginia. It was really hot in the summer, and I exercised a lot. When I came back, I wanted the place cool, so I would turn the AC down to 68. He'd come in and get really mad. Put it up to 75, and I'd put it back down to 68. I've learned to be more energy conscious. So what we do now is we locate on the psychrometric chart the different states that our system has to meet, or states that are in our system. So we've got the outside condition. Now we want to put the indoor condition, and that's going to be 7250. So come down to 72, and we go up to the 50%. Right there. Now this little mark here represents a kind of a suggested design, indoor design condition, which is even warmer than 75. It's 78 and 50%. 78 and 50%. You might see that in Japan, where they keep the room temperature, room conditions quite a bit warmer than we do here. But we're going to be a little bit cooler. Okay, so that is, we're going to call that our return air, because that's the state at which the air is going to be drawn into the system in a normal air conditioning system. Not this one. This is an abnormal one. Right? So generally, let me show you a typical office building or department store, larger kind of building. What we would do is we would draw air out of the room. This is stale air. It's got carbon dioxide and all the toxins that might come out of the lab or that we emitted into the space. If all we did was recirculate this air, over time it would become pretty bad, wouldn't it? Especially on a hot summer day, warm summer day. And so what we do is we mix some of that, we draw some of this air in, and we exhaust some of it. We return some of it and we exhaust some of it. And however much we exhaust, we'll make it up by drawing in outside air. And so what we end up doing is our air conditioning system will mix the outside air with the return air. So we will connect them with a line like that, and the mix point, the mixture will be based on the relative proportions of the return and the outside air. If it were 50%, if our air coming in was 50% outside and 50% return, we'd be right on the middle of that line there. And our mix air, we could figure out what the temperature of that mixed air is by just coming down and reading it. A normal system would have maybe 30% outside air, so we will be closer to the return air condition. And our point would be somewhere closer, maybe down here somewhere. But anyway, that gets into mixing, adiabatic mixing of air streams, and we'll talk about that later. Right now, we're just going to assume no mixing. We're just going to take pure outside air, and we're going to condition it from here to here. Now, I'll tell you right now, we can't do this with a real air conditioner, and the reason we can't is suggested by these lines here. These lines show typical conditioning processes, where we take air and we cool it. So if you take, for example, you've got air going into your conditioning unit here at what, 100 degrees and 110 grains of moisture. When this goes into the air conditioner, what's going to happen is this air is going to come into contact with the cold refrigeration coils, and it's going to cool. It's going to cool sensibly, and it's going to keep cooling all the way until the air that's closest to the coils. So if you can imagine looking at a cross-section of coils, and you've got refrigerant going through these, really cold refrigerant. This refrigerant is evaporating as it absorbs heat from the air. So you've got warm air, and then cool air coming off. We can even calculate the Nusselt number. We learn how to do that heat transfer. You know, a bank of tubes, remember that? In internal flow. Okay, so I've got the warm air coming in. What's going to happen is we're going to have layers of air. We're going to have air that's right in contact with the tubes. This air is going to cool first, and it's going to cool the most. And then as you get further away from the tubes, the air is going to be warmer. So you're not going to have a uniform spread of temperature and conditions. There's going to be a gradient with colder air closest to the refrigerant tubes, and the coldest air right on the surface of the tube. Okay, there's actually there's a term called the apparatus dew point temperature that defines the temperature right on the surface of the tube. And the manufacturer, this is something you get from the manufacturer, and we can use it in our designs, called the apparatus dew point temperature. And that'll pop up later somewhere. I think we'll introduce that. But so the point being here that as this air comes in, on average, this is like the average air. The air is going to come in, we're on this line here. It's going to cool, okay, and then what's going to happen is the air that's right, it's right on the tube, and near the tube, is going to go all the way to saturation, and then condensation happens. Then you follow the saturation curve there, okay? Because you can't, once you get to saturation, then the moisture drops out, and you can get cooler, but at the same time you're getting cooler, you're condensing water. The water's going to collect out, and it's going to drip off those tubes. But as you move further away from those tubes, the air's going to be warmer, and you're not going to have condensation. So this represents a sort of average behavior of the air. As it approaches saturation, it starts to curve gradually down like this. Some of it's going to be over here, and some of it's going to be a little bit warmer because it wasn't able to get close to the tubes. But the average behavior is going to be like this. And it's going to come down. So if you want to go to 70 degrees, 72 degrees, the path that we're going to take from here is not that. The path that we can engineer is going to take us like this. It's going to take us over to close to saturation, and then we're going to drop down and condense water, and we're going to come down like this. And then if we want to get to 72,
You have to heat it again.
we're going to come down to somewhere about right there. Now, I'll tell you right now, when you come off of an air conditioning coil, the air that's right on the coil is going to be at saturation, so it's going to be at 100% humidity. But on average, it's going to be about 90%. So a design target coming off an air conditioning coil is, the design target is that air at 90% relative humidity, and whatever temperature you want is going to be. Or 90% humidity and whatever the moisture, the humidity ratio has to be to help you get back to your goal here. So our conditioning, we're going to come out of our air conditioner somewhere over here. Whoops. Let's see. 90% humidity and 50, 51, 52, 54, 55, about 55.5 degrees. That, a real air conditioner, to get me here, is going to have to cool the air down to 90% relative humidity and 55.5 degrees. And then what I have to do to get to my desired state is I've got to reheat the air. And this is something that we don't like, because this is wasted money. This is wasted energy. You got a really hot day outside and you got all the heat you could ever want out there, but now we've cooled our air to the point where it's 55 degrees. And but we had to cool it to 55 degrees in order to get to our desired humidity and dry bulb temperature, and then we have to sensibly heat it back up. So often in air conditioning systems, they're actually designed with, there's your duct, there's your airflow, they'll have a your cooling coil, and then there'll be a heating coil afterwards for reheating. This is dumb. It's just not a nice way to design a system, but that's what we would have to do in this case. But in the example, just for simplicity, we're going to add this part in later, because that's how we really design a lot of the simpler types of systems. But right now, we'll make believe that we can, in fact, do a direct cooling, and this is just really to show us how to do the energy calculation. Oh, shoot. I guess I could have defined that last state as over here, but we'll leave it there. Okay? Okay, well, what we would really do is this. We would take some outdoor air, take some return air, we'd mix them in a mixing plenum somewhere, maybe in the ceiling, and we would produce a mixed point, maybe somewhere here. If we were 30% outdoor air and 70% return air, and that is what we would condition. This would go into our conditioning unit. So this would be the air coming off our conditioner, and our actual conditioning process would follow that line. It would go all the way over, and then it would curve down until we got to C. But in our when we represent these on the chart, usually for the sake of simplicity, we just draw straight lines, even though we know that that's not actually what's happening. So we have something like this. Okay, so we would bring return air, mix it with outdoor air, producing a state M, which is mixed air, and then the mixed air would go through the conditioning unit, and that would be our air conditioner right there. That's our conditioning unit, bringing us to a nice cool 55.5 degrees and 90% relative humidity, and then that would dump into our room. So you put your hand up by the vent, or the grill that's pushing the air in, and you'll feel 55 degrees. Feels cool in an air conditioner, right? And then as it comes into the room, it will, sorry, I forgot something here. Oh, yeah, so that's, so as it comes into the room, it will warm up like this. Actually, it won't, because this is showing the reheat. If we dump this into the space, it is going to, that cool air comes in and it mixes with the air in the room, and it absorbs the heat and the moisture in the room. And as it does so, it it'll move at an angle upward like that. But I'm getting ahead of myself, and I don't want to go there quite yet. So, but I just wanted to show you something more real. But now let's do the calculation. So we've got our return air state. So the first thing we want to do is get the necessary properties. So at R, what we really need, the two properties we need are the humidity ratio and the enthalpy. So the humidity ratio looks to be right there,
59.
52, 658. Per pound of dry air. I could probably do this more accurately if I was on paper, but with a marker and the whiteboard, sacrificing a little accuracy here. So that W looks like about 58 grains. So let's divide by 7,000. Let's see what we get. .00083. Does that sound about right? Yeah. All right, and then our enthalpy for our energy balance calculation is, let's see, we connect the 25, where's 25? 25 and 25, and let's see, 26, 26, 27, 25, 26, 27. So 27 is too high. 26.5. Wow, it looks like right on, doesn't it? 26.5.
Yeah, I think it looks like
26.5. Okay. All right, so we have the necessary information to figure out our energy, do an energy analysis on our air conditioning unit here. The final thing we need is the flow rate of the air, and that's given as 500 CFM. Okay, so now we want to figure out how much energy, the rate of energy removal and the rate of water removal, because we're cooling, we're obviously reducing the enthalpy, but we're also reducing the water vapor component. Okay, so how do we do that? Well, now we're going to do a first law analysis. Should have given myself more space this out better. Okay, so this is what we have. We've got an air conditioning unit. And this unit has a refrigeration coil. Okay, so this is the source of cooling. We have a refrigerant coming in as a saturated mixture. So it's coming off the throttling valve. It's cold, and its quality is about 0.3. So it's going to come in and go around, and it's going to acquire the warmth from the air, and it's going to come out as a saturated vapor. So we'll look at the refrigerant side a little bit later, but now we're just interested in the QL, the heat that's going out of the air and into the low temperature reservoir, which would be the refrigerant. So we have our outdoor air coming in, and we have our return air going out to the room, and this is going to be our, this is our T equals 93.5 degrees, and T equals 72 degrees. And our moisture going in was 0.0206. And our enthalpy was 45.1. And our specific volume, 14.41. And then coming out, we come out at 0.0083. And our enthalpy is 26.5. Okay. So that's a diagram of our system. I'm now going to erase this to give me some space. Okay. So now we have an air conditioning system, a little air conditioner. This might be a good model for well, it comes close to maybe a car air conditioner, but even a car air conditioner is going to have some mix of outdoor air and air from the compartment. Although you can adjust that, you can make it so it's only outdoor air coming in. And there are specialized air conditioners called dedicated outdoor air systems, or DOAS, that don't have any return air. All the return air is exhausted. So it's a once through. You push the air into the space, and then it's sucked out and exhausted and replaced with all outside air. Those are becoming increasingly popular because they are, you use those for humidity control. The sort of the state of the art now is to separate humidity control from temperature control. We have two separate systems. One system controls the temperature, dry bulb temperature, and a separate system does the humidity stuff. That seems to be more energy efficient than a DOAS system. Is a good humidity control. Okay, so we want to do a balance, energy balance here. First law of balance. So we've got warm stuff coming in. This refrigerant is going to carry out heat. We'll call that Q conditioning. This is the heat that we're removing. And because we are dropping the temperature below the dew point temperature of the water, we're going to condense water out at some mass flow rate C. Okay? Now, this water that is condensing exits the conditioner at something close to the exit temperature from the conditioner. And yeah, this is really good. Normally we would call this supply air because it's coming out of the conditioner. It's supply air to the room. But this is kind of strange to do it like this. I hope I don't end up confusing you by doing it this way. Okay, so this, this air, this water comes out at the exit temperature here of 72 degrees F. Okay? So now we want to do an energy balance, our first law balance, which of course says energy in equals energy out at steady state. So what do we have going in? We've got the outdoor air going in, and it goes in at mass flow rate of dry air times HOA. That's our energy, the rate of energy going into our air conditioner. And that's it. That's the only thing going in that has energy. And then coming out, we have QC. We have the energy in the air that's leaving. And I should also say that in air conditioning, we always have to keep in mind we have two fluids. We have two different fluids flowing here. We've got air, so we've got a mass flow rate of air, and we have a mass flow rate of water. Now there's only one mass flow rate of air. We're not messing with the air, the dry air. It's constant going through the system, and it is in most systems. Whatever dry air you have going in is going to be the dry air coming out. It's the water flow that changes. We mess with the water flow. So coming out, we're going to have mass flow rate of air and mass flow rate of water for the return. And because we're condensing water, this water is going to be less than, sorry, this is mass. It's going to be less than the mass of the water going in, right? Okay, so we've got, there's our heat leaving, and that's being carried away by the refrigerant. We've got the energy being carried away by the exit air, and we've got energy being carried away by the water. So you've got to factor in the water flow that's leaving, and then the enthalpy of that water at 72 degrees F. Well, it could just be HF because it's liquid. So that's our energy balance for our air conditioning. Now our mass balance, we have mass of air going in. We can write it as, if we want to do this formally, mass of air in the outdoor air plus nothing. We're not adding or taking away any air, and that's equal to the mass of the dry air coming out. And so we just call it mass of air because it's constant all the way through. Something we saw in a lot of our thermo problems where you just have one stream in and one stream out. So that's our air balance. And then our water balance is the mass of water going in equals the mass of the water coming out plus the condensate, right? Water in equals water out. Now we're interested in calculating what this condensate flow is. So let's go ahead and solve for that. So it's just the difference between the water going in and the incoming air and the water leaving in the exit air. And this can be written as in terms of the mass flow rate of the air times the humidity ratio. And this is an equation that we'll see quite often because it's telling us how much water we're going to drain out of our air conditioning, how much water is being pulled out of the air that we're cooling. So it's the mass flow rate of the air times the difference in the humidity ratio between the two streams. Okay? And now let's do the same for our energy balance. We're interested in QC. And because we've just solved for MC, that's here, we can replace this MC with this MC, and we end up with our energy equation, M dot, or MA, so there's our energy balance. You see how we do that? It's based off of our diagram here. The condensate flow rate and the heat removal, all in terms of properties that we've already found or that we can look up or calculate. Now the property we still don't know, we don't know the mass flow rate of the dry air, and this we can look up. Any idea how we get, yes?
Oh, what's that enthalpy term again?
Hmm?
The at 72 degrees. What was the subscript stand for?
This is the enthalpy of liquid water at 72 degrees. Okay, so we can look that up in our table. And I think I have that open here. We just go to water at 72 degrees. So here's 72 degrees. Enthalpy of vapor, enthalpy of the liquid is 40. 40.077, we'll call it 40.1. Okay. And how about the mass flow rate of dry air? Any idea how we get that?
Could you divide the CFM value by the specific volume?
Yes. Great. Yeah, so let's see. That's where our flow rate comes in. Q is 500. We're bringing in outside air at 500 CFM, and we know what the specific volume is. Remember, volume, mass is equal to volume over specific volume, or density times volume, right? So our mass flow rate of air is going to be equal to our CFM multiplied by our specific volume, or divided by our specific volume, which is 14.4 of our entering air, 14.4 cubic feet per pound mass, or per pound of dry air. And you can see how this comes out to be exactly what we want, dry air per unit time. But we want this in hours. So I'm going to convert to hours. This is minutes here, 60 minutes in an hour. And so this is going to be, we're almost done. The last thing we need. So 500 times 60 divided by 14.4 equals 2,083 pounds of dry air per hour pushing through our system. Okay? Now we've got all of the variables. Plug everything in. So I'm going to go ahead and write the mass flow rate of the dry air is 2083 pounds of dry air per hour. And we'll turn this off and open up some space here and finish out our calculation. Got 1 minute. Okay, so our mass flow rate of condensate is mass flow rate of air, which is 2083 pounds of dry air per hour. And then WOA is 0.0206, WR 0.0083, and the units are pounds of water per pound of dry air. So that's going to give us pounds of water per hour, and that's what we want. So we don't have to do anything more. So times minus can't be right.
I think
Thousands of pounds of water.
Yeah, I think, don't you have to multiply the W by HF?
Oh, that's for the calculated Q. So 25.6 pounds of water per hour, and then QC is 2083 pounds of dry air per hour. And HOA is 45.1, HR 26.5, and the units there are BTU per pound of dry air. Okay, so now minus, let's see, that's going to be in brackets there. So minus WOA. WOA is 0.0206 minus WR 0.0083, and that's units of pounds of water per pound of try air multiplied by, sorry, I messed up. Going too fast here. Which are MC. MC was 25.6 pounds of water per hour, and then HF at 72 degrees was 40.1. Pound of water. Okay. So let's make sure we've got our units straight. We need to have BTU per hour minus BTU per hour. So this is pounds of dry air cancel, BTU per hour, pounds of water cancel, BTU per hour. So that looks good. And let's see what we have here. So 45.1 minus 26.5. Then minus 25.6 times 40.1 times 2083. Adding or subtracting?
Adding.
This is subtracting. So subtract. So about 2 million BTU per hour. So we want to convert this to tons. Minus 170. I think I did something wrong here.
Yeah, I think the units are different.
Yeah, I need to check. Yeah, let's come back to this on Wednesday. I want to check through and see why my numbers look odd here.
Are you?
But that's the
okay if I keep
setup
the
of
chart?
the energy and
You okay if I
the
keep
mass
the chart?
balance on the conditioning unit.
Thank you. Okay, sounds good.
That's where you want it.
Can I collect your classwork now?